This is what we did last time. Got a lot of definitions of vertices, the number of edges, number of vertices, the degree of each vertex. That is, if this is a vertex, how many edges come into it? 1, 2, 3, 4. And so the degree would be 4. And then based on whether in a graph you have, the nature of the degrees of the vertices, you could have an Euler path. But remember, to have an Euler path, you must have 2 odd vertices only. I should say at most 2 odd vertices. And then to complete the path, you'd start at one of the odd vertices, vertices, and then you'd end at the other. And the reason for that is that if you're doing a path and you come into a vertex, you either stop there, which would give you a degree of 1, or it's kind of in the middle of your path and you have to leave it. So if you enter and exit that vertex, every time you enter and exit, there's 2 different edges that are counted. And so it's only the very first one that you would start at if you wanted to do a path. That could be odd, and the other one, and the one that you end with could be odd. All of the vertices that you visit in your path along the way, you're going to be entering those vertices and exiting those vertices. And so you have to count the degrees in terms of 2's, except the beginning and the end. And then for an Euler circuit, all of the vertices have to be even, because it's just an Euler circuit is an Euler path. But just imagine that you had that Euler path where you began somewhere and you ended somewhere else, so that you had only those 2 odd vertices. A circuit would just require that you join the ending point back with the beginning point, and then that makes those 2 odd vertices even. So for example, this one here, if you write down the degree of all of these, you'll find that the degree of every single one is even. No, that's not true. Here's an odd one. And there's another odd one. Everything else, however, is even. I think I have them all. So all even numbers except here and here. So this means that there is an Euler path. Is there an Euler path? Yes, because you have 2 odd vertices. And what you would need to do to actually traverse that path is to start at one of them, either this one or this one, and then end at the other one. And then this one down here, I think, is the one that has all even vertices. And if you have a graph that has all even vertices, notice it's the same exact graph up here, but they connected this one here with this one over here, making now this vertex over here have degree 4, and this one also having degree 4. So they're all even, and if they're all even, then there's an Euler circuit. So the Euler problem was the problem where you want to traverse every edge in the graph, and you don't want to you can visit the vertices more than once, but you can only visit an edge once. You don't want to do any backtracking. So what's interesting is to actually try to do it. And unfortunately, you have one attempt, because if you don't make it, then all right, so I'm just going to try it here. I'll start here and go here, here, here. Notice I'm revisiting this vertex. Here, here, there, 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 there. Just trying to work my way, weave my way around from left to right, or from right to left, I guess I'm going. And eventually you get there. Start and end. And then what I would do down here is the same exact path, but once I get here, then I'll jump over here to end at the same place where I began, and then that completes the circuit.